Hello everybody, it's Albert here today, and this is my research project that focuses on Euclidean rhythms and rhythmic oddity. This project uses mathematical music theory in the sense of creating rhythms by using two algorithms, the Euclidean algorithm and Berjorklen's algorithm. Moreover, these rhythms are displayed geometrically, and in addition, it can represent a famous rhythm used in certain countries. Before we dive in, we must know that a rhythm contains the following: beats, rests, and pulses. Let's start with Euclidean's algorithm, which is an algorithm developed by a Greek mathematician by the name of Euclid. Using the process of division, this algorithm involves computing the greatest common factor between two integers, especially those that are not a factor or a multiple of each other. The smaller integer is divided into the greater integer, and the process continues until there is no remainder left. Let's take a look at this example. We have 7 and 5, in which 7 is the dividend, or the total number of pulses, 5, which is the divisor, or total number of beats. We divide 7 by 5, and our answer is 1 with a remainder of 2, and the remainder represents the number of rests. The same thing applies to the remaining steps. Regarding this example, the greatest common factor is 1, and as you can see, this rhythm is being represented on a rectangular figure with boxes either containing an X or a beat or no X, which represent rests. Let's move on to Berjorklen's algorithm, which involves binary representation. Using the expression n minus k, we are given two integers in which n represents the total number of pulses or the total number of zeros and ones, k represents the number of ones or beats, and the number of zeros, which are rests, is the difference between n and k. We then line up all the ones and zeros separately. We then place a 0 after every number 1, and we continue this process until the rhythm is represented as evenly as possible. The rhythm is then displayed on a clockwise figure, which contains dots being connected with lines, creating a certain shape inside the circle. The numbers with dots represent beats, and the numbers without dots represent rests. Speaking more of clockwise figures, the rhythm can be represented by a necklace, which is a mathematical object defined in terms of equivalence classes. The members of the equivalence class are considered the same rhythm, written in a different way. Also, depending upon the shape, it can represent the rhythmic oddity property. For a rhythm to satisfy the rhythmic oddity property, it must have an even number of total pulses, plus the shape inside the clockwise figure must not be evenly cut in half. Looking at these two examples here, the first rhythm, the acapygmies, satisfies the rhythmic oddity property, while the second rhythm, the seguiria, does not. Last but not least, there are some rhythms that are maximally even and do not satisfy the rhythmic oddity property, and some that are not maximally even but satisfy the rhythmic oddity property. Regarding these rhythms on the right, the first one is maximally even since the number of pulses between each beat is 2, but does not satisfy the rhythmic oddity property since it can be divided evenly. On the other hand, the bottom rhythm is not maximally even, but satisfies the rhythmic oddity property since the shape cannot be evenly divided. Now that concludes my research project.